What were congruences? What were we worried about? Congruence was a notation for expressing, so we had an expression, something like AX is congruent to B mod M. What did that mean? That meant very simply that A times X minus B is divisible by M. Or equivalently, the alternate way to think about it is that the remainder of AX divided by M is the same as the remainder of B divided by M. Okay? The congruence notation gives us a way to talk about basically the divisibility properties of classes of integers. It's the fact that for any divisor, okay, if we're talking about the remainders with respect to a particular divisor, okay, it's certainly clear that if we want to say what is it that has a remainder of 1 when you divide it by 10, well, the answer is it's 1, it's 11, it's 21, it's 31, it's minus, okay, what has a remainder that's less than 0? My claim is if you count back 10 from 1, okay, what is it that's going to be? It's going to be minus 9, okay, minus 18, minus 9, minus 19, minus 29, etc. Okay, so the point is that this notation lets us define a set of integers, all of which are have identical remainders, and the congruence notation gives us a way to talk about that. Okay, any questions about what we mean by the congruence notation from last time? Okay, and we saw that again, we could do arithmetic in certain ways. We could take two congruences and add them. We could take two congruences and multiply them. We could take two congruences and subtract them. We could take two congruences, or we could factor something out of a congruence, provided we were very careful about how we dealt with the modulus. There was a different case, remember, between whether or not what we wanted to factor out was something that divided the modulus or not. Okay? And that was sort of the key trick to working with these things. Any questions about what we did last time? Okay? So hopefully we got the basics of working with congruences last time. We also saw an application to graphics, and so hopefully people are convinced that they're a good thing. Well, one thing that you need to do with congruences reasonably often, or one important property, is to try to solve equations involving them. Okay? So suppose we have a formula of the form A times X is congruent to B mod Y. Okay? B mod M. Okay? We want to know how many solutions are there to that. Let's say A is a constant and B is a constant. X is a variable. Certain values of X may or may not satisfy that congruence. Okay? Question is, which values satisfy that and how many of them are there? Okay? And it turns out that there's three cases of interest. Okay? The first is, how many solutions are there? Obviously, if we have one solution, mod M, okay, presumably we have other solutions that are, one solution for X, okay, there's presumably going to be other solutions that are bigger than M. So let's talk about just restricting the solutions to X where they lie between 0 and M minus 1, since no numbers bigger than M sort of exist in the mod world. Any questions? Okay, suppose A, okay, our multiplier, and M, our modulus, are relatively prime. How many solutions does AX congruent to B mod M have if A is relatively prime to M? The interesting thing is we worked that one out last time. Okay, if you may remember last time, I showed you the amazing property that if A was relatively prime to M, AX is going to be congruent to B. I mean, remember, the set of numbers, A times 1, A times 2, A times 3, A times M minus 1, all of them return distinct integers between 0, between 1 and M. And obviously, the remainder of 0 mod M is 0. So the point being that for if A was relatively prime to M, the fact that the spectrum of solutions we got for this to find the permutation meant that there had to be exactly one solution for any value of b. Okay? That's really just another way of saying exactly what I was saying before. Okay? The fact that as we count through this variable, if this is relatively prime to that, we get a different, each time we would get a different value of b. In fact, there are m choices here. There are m different possible values of b relative, since if it's something that's greater than, b was greater than m, we could simply take that mod m, and it would, subtract out m from it, and it would still be the same residue, mod m. My claim is that if a is relatively prime to m, this expression has to have exactly one solution. How many people believe that? Okay? How many people do not believe that and want more explanation? Any questions? Okay? So good. So we now know how many solutions there are for that. What if, on the other hand, now they're not relatively prime? That means that the greatest common divisor of the multiplier and the modulus is greater than 1. If they're relatively prime, the greatest common divisor of the multiplier and the modulus is 1. Okay? So we're going to distinguish two cases. Does this greatest common divisor divide b, our constant, or not? Okay? Suppose it does not. Suppose that g divides a, okay, and g divides m. Okay? And we want to now know, okay, maybe let's zoom it away just for a second so we get this thing on here. We know that g divides a, g divides m, g does not divide b. My claim is that there are no solutions in this case. Why? Well, let's take a look at it. We know that if we have a solution, by definition, m, what does it mean to have a solution? That means that ax minus b is divisible by m. Okay? So we know that that's true. We know that the greatest common divisor of a and m has to divide m. Therefore, the greatest common divisor has to divide ax minus b. How many people follow the logic so far? Okay, anybody confused so far? Okay? So now we know that g divides that. But what do we also know? We also know that g divides a times x. Why does g divide a times x? Because g is the greatest common divisor of a and m. G has to divide a. So clearly g divides a times x, correct? But what do we know? We also know g does not divide b. So now we know that if suppose g divides ax and g does not divide b, is it possible for g to divide ax minus b? Okay, the answer is no. So inherently we have a contradiction. Okay? And so therefore there can't be any such solution that we have there. Okay? Any questions about that? Okay? So again, to sort of show why that something like that might happen, take a look at this one here. Are there any possible solutions to the equation? 2x is congruent to 1 mod 4. Again, the greatest common divisor of these two is 2. Okay, I think it's pretty clear that 2 times x is going to leave us with an even number. Okay? Again, okay, so if x was 0, we would have 2 cannot be congruent to that. If x was 1, okay, 2 times 1 is going to be 2. If x was 3, 3 is 2 times that's 6. 6 mod 4 is going to be 2. If x was 4, 8 mod 4 is going to be 0. In none cases there are 1. Okay, there's no solution to that congruence. Any questions? Okay, good. Now, suppose, let's say, we have the third case, which is that we do have a greatest common divisor of a and m. Okay? That's not 1. But in fact, g is divisible by b. Okay, g divides b, excuse me. Okay, that the greatest common divisor also divides the thing that's out there. Okay? Now, in this case, we have a congruence of the form where there's a greatest common divisor between this, this, and this. We showed last time that if we do have a greatest common divisor, a divisor that divides out between all three, we could in fact divide out, we showed last time that we could in fact divide out across that congruence. Okay, I don't think I'm going to show it again, but we showed that before. Okay, so my claim is now we know that we have a congruence of that this congruence. Okay, that if this is true, then in fact this is true. So now we have a simpler congruence, a congruence with smaller numbers. Okay, and in fact a congruence where there is nothing that divides this last thing. Okay, if we take out the greatest common divisor of this, it's not going to be one of the cases we had before. Okay, correct? I mean, it's going to reduce to one of the cases that we had before. Okay, so if we divide this thing out, the greatest common divisor by all of these, okay, what's interesting here? Which case is going to apply? Well, my claim is that A is going to be relatively prime to M, because once you divide A and M by the greatest common divisor, what's left has to be relatively prime. Okay? Everybody should believe that. Okay? So now what do we have here? Now we've got a situation where, because this is relatively prime to that, this congruence has exactly one solution in the range that it was supposed to, the range mod M that it had. Okay? So if we take that one solution, that solution is going to range between 0 and M over G. The original question was how many solutions were there from 0 to M, okay, or M minus 1. So if we look at this, if we consider that any integer, suppose we know that x prime is that solution, any addition of a multiple of M over G plus x prime will be a solution to this second congruence. Correct? If we go back to this thing, and suppose I tell you to x, make x be something that satisfied this, and I add another m plus g to it. Adding an m plus g to this side, okay, if it was already divisible by m by g, adding another m by g is not going to change its divisibility. So the point being that we can now have any multiple of m plus g added to that. And there are g such, okay, multiples we can have before the number gets too big to fit in the interval from 0 to m. So my claim is that there's one solution, base solution to the simplest congruence. It can be expanded g times while keeping those numbers within the original interval. So that gives us a total of g such solutions. Any questions? Again, maybe it's easier to see the example to see what was going on. Suppose I want to find all solutions to 12x congruent to 18 mod 30. Okay, I can divide by the greatest common divisor of this and this. What is the greatest common divisor of this and this? Okay, 6. That leaves me with 2x prime plus 3 congruent to 3 mod 5. Okay. This thing, there's only 5 possible x primes that are interesting here, correct? We could try 0, 1, 2, 3, or 4. Okay, if you try 4, you'll see that 2 times 4 is 8. 8 is congruent to 3 mod 5. The unique solution here, we knew there can only be one. In fact, we find it by brute force. It's 4. So 4 will satisfy this congruence. The other thing to see is that 4 plus 5 will also satisfy this congruence. Okay? Correct? If we now make that 4 plus 5, that's 9. That's going to be 18 congruent to 3. 18 minus 3 is 15 mod 5. Any multiple of 5 we can add to it, it'll be fine. So in fact, there's a total of, we can multiply 5 by up to the greatest common divisor times. We can add up to, from 0 to g minus 1 instance of the modulus. Okay, and that gives us our spectrum of solutions. Any questions about that? I may have done that a little bit more detail than I needed to. But my claim now is that we now know if I confront you with a congruence, you now should know how many solutions it has. Okay? Any questions? Okay. Once you know how many solutions you have, that's a good thing. But in general, okay, if I ask you for a solution to a congruence, and you say, well, there's one answer, okay, that's nice, but you usually want to know what that answer actually is. Okay? So what's interesting is, we can, we now know how to count the number of solutions to a congruence. We now know that if we have more than one solutions to the congruence, we can divide by the greatest common divisor of this and this to reduce it to a problem where there is only one solution. Okay? And we know, once we have that one solution, how to expand it back to give us all the solutions that we would have. The thing that we haven't shown you, okay, yet, is how do you actually find what that value is? We know that this is relatively prime to this, okay? This thing, therefore, has one solution. What is that value of x to do it? What is the simplest way to do it? Let's just make sure everybody sees. Can somebody give me a procedure to find out what that value x is? Okay? Any idea how you could find out what x might be? Okay? Simplest procedure, really stupid procedure. Okay? Try all possibilities. Okay? When in doubt, use brute force. What's interesting about what's very interesting about modular arithmetic is that you're never going to have to worry about any value of x that is larger than the modulus. This is a finite-sized problem. If I ask you, here's some equations, okay, and if we forget about the integer arithmetic, back if I gave you a linear equation to solve, and ask you, try all possible values, give me, and to try to solve that equation by brute force, if you have an unbounded number of solutions, because the answer might be real, or the answer might be an infinitely large integer, you'd be in trouble. But here we're in an integer world and a finite integer world. Notice that, let's just look at this example just to make sure everybody sees this thing. Suppose I know that x is a solution to this. I claim that x plus 2151 is also a solution to this. Why? Let's multiply this by 863 minus 880. Okay. We know that if we didn't have this, okay, and we take this, divide this by 2151, if x was a solution, actually I don't know if this is this visible or is this, okay, it's visible. We know that if x was a solution, this minus this was divisible by this. If I now add to it 2150, the denominator times something, it's still divisible by it. So the important thing to see here is you get no points for testing integers that are larger than the modulus. We know that there's a solution. We know that there's a finite bound. Okay? The simplest procedure is to realize that brute force will suffice. Okay? It's not necessarily elegant that if the modulus is very large, you're in trouble. Okay? But at least we're living in a finite world. Any questions? Okay? In fact, there's actually a more elegant way to solve this problem, okay, and a better way than just brute force, although it's good to know that you can rely on brute force if necessary, okay? What we can do is reduce the problem of solving this congruence, okay, to a problem on a smaller modulus. Remember Euclid's algorithm for finding the greatest common divisor. We had an iterative procedure where we kept chopping things down until eventually the answer was clear. We can have a similar procedure to find the solution to this congruence. Okay? My claim is that if you want to solve the congruence AX congruent to B mod M, it suffices to solve the congruence MY congruent to minus B mod A. Okay? Why is this an improvement? Because A has to be less than M to be interesting. Suppose A was greater than M. Okay, would that have made any difference if we made it smaller? Okay? Again, let's go back to here. Here we had A was 861, this thing. Suppose I make it this plus 2153, this plus the modulus. If we had a solution before, okay, multiplying this by 200, adding another, if all this was already divisible by this, okay, adding an extra 2151, x plus whatever I had here, divide that by 2151, this is clearly still divisible. So the important thing to see is that if you start it off without loss of generality, we can reduce a to below the modulus of m, to a number less than m. By doing this transformation, if you trust me that it works, and if you don't, I'll prove it in a minute, we've got into a world where our problem is easier, okay, because this is strictly a smaller number. Any questions at this point? Okay? Well, what's interesting about this? My claim is, suppose you solve this congruence, okay? This congruence, which is an easier congruence, okay? Suppose we know that y is the solution to this congruence. I claim, in fact, that x equals my plus b divided by a is a solution to this. Okay, so if you have a solution to this, you can work back to a solution to that. Why is it? Let's take a look at that. Suppose we know that we have a y is our solution to this. What does that mean? It means that my is congruent to minus b mod a. What does that mean? An equivalent way to state that is that a divides my plus b, correct? That's just a restatement of this. Okay, and this is just a restatement of the fact that y is a solution to that. Well, what does that mean? That means, I claim, that we can, if a divides my plus b, that means that there is some integer x such that x times a is equal to that. Right? That's what it means for, say, something divides this. Okay, it means that when you divide this by this, you get an integer. Let's call x the remaining integer. What does that mean? Well, in fact, we know not only is there an integer, but we know that x happens to be my plus b. Now let's go back to here. Okay, we know that x is an integer. We know that this is an integer. My claim is this satisfies the first congruence. Why? Let's plug my plus b over a into here. We multiply that by a, we get, what's left is going to be my plus b. Is my plus b congruent to b mod m? Certainly, because my plus b minus b is my. My is obviously a multiple of m. Therefore, it satisfies that congruence. Okay? So my claim is that if once you find a solution to the smaller one, that will give you a solution. You can work backwards to get a solution to the bigger one. Okay? Any questions or comments on that one way or another? So one solution, this way to solve your congruences. Okay? This in some sense gives you an algorithm to solve your congruences. Okay? We're going to take our thing and keep chopping it down, okay, to make it easier to work with. You want to solve what you want. You want to solve 8, the congruence I had up there, 863x congruent to 880 mod 25 this. Well, what do? If you remember, the reduction was make b minus, make this my, make this the modulus. Now that we've got this my here, m is bigger than the modulus, we can reduce it relative to the modulus to get something smaller. Okay? What is the remainder of 2151 when we divide it by 863? How many times does 863 go in there? Looks to me like it's twice. Okay? I mean, let's just make sure I did the algebra right. Okay, how do you get that? Well, 863 times 2, if I remember correct, is 6, 12, 17. 2151 minus 1726, 4. That's going to give me a 5. It's going to give me a 2. That's going to give me a 4. So this congruence is identical to that because I can reduce the bigger one. Okay? Any questions about that? That's important to see. Now I know that I can, given the answer to this, okay, I want to try to simplify it. Now I can make this guy the modulus. Okay? Again, 880 is now bigger than this thing. I can chop that down to 863. Okay? Minus 880. Okay? Minus 880 I claim is 846. That's something you should be able to do. Okay? So actually, how would we go about doing this? Okay? The way that you could convert this, if you want to convert that minus 880, we can add an 863 to it to see where this number comes from. Adding an 863 to it will leave that unchanged. So we can add one 863 to it, and we still got a negative number. Add two 863s to that, then we'll get a positive number. I think it should be clear that minus 880 plus 2 times 863 is 846. Okay? So that's how we reduce the negative to a positive. Okay? You don't just ignore the signs because that'll get you in trouble. Okay? Any questions about that? Okay? It's important to see that it's always safe to add or delete any multiple of the mod on either side. Any questions? So what do? We now have the problem reduced to this thing. Okay? Again, we can now flip this thing, make this the modulus. By similar analysis, we now get 13 as a base. Okay? What we're left with now is something that looks like, again, let's say at the end, I come down with something that's 9w is congruent to 9 mod m. In this case, what you should know is that because 9 is relatively prime to, the 9 is clearly the greatest common divisor of these two. This is relatively prime to the modulus here. Eventually now we've got down to a point where it's telling us that w is congruent to 1 mod 13. Now you've got it simple enough that you can solve it. Then I claim by going back and doing the substitutions, you can go back and figure out what the original solution was. Any questions? Okay, I don't want to go and do all the algebra. The interesting thing to see is how we did the reductions corresponding, depending on what the current modulus was, and how we ultimately came to a situation where we solved the last one. This thing is solved once the coefficient of w or the coefficient of this variable is 1. Okay? And here we were able to just get it by dividing. If not, we could have gone through and done a couple more iterations. Eventually we would have gotten there. Any questions? Okay? So now I claim you all should know how to solve a congruence. Okay? Or at least be able to look it up and figure it out. Okay? In principle, we now know what congruences can be solved, can't be solved. Okay? And how you go about doing it if you have to do it. Any questions? Okay? Good. Now, sometimes we're confronted with solving not one congruence, but many congruences. And in fact, many congruences simultaneously. Okay? Suppose I tell you that my lucky number has the property that when you divide it by 5, you get a remainder of 1. And when you divide it by 2, you get a remainder of 0. What is my lucky number? Okay? Really what it is saying here is that you've got two different congruences. Okay? And the question is, each congruence defines a set of integers that satisfy it. What are the positive integers that satisfy this? Well, 1 does. 1 plus the mod does 6, 11, 13, ... Which are the ones that are, what are the integers that are 0 mod 2? What are those integers? The evens. Okay, so it is basically, what is the even number? So basically, 6 would satisfy this. And I claim some other numbers would also satisfy. What's the next number that will satisfy this? Okay. This is going to describe 1, 6, 16. The next one would be what? The next one would be 11, 16. 16 will also satisfy both of these, right? What's the next one that will satisfy both of these? 36. If you look at it now, we've seen something interesting. This particular system of congruences, in fact, it's clearly solved for x equals 6. It's also solved for every 10 numbers, which happens to be the product of the two moduluses of these systems. So it should be clear that once you have a solution, this is a solution that's going to repeat for sufficiently large numbers. Okay, and I believe the product of these two is a safe bet. Okay? Any questions? And maybe the least common multiple, in fact, I think is where things will start to repeat. Okay? Any questions? Sometimes there's systems of congruences that don't have any solution. Okay? For example, suppose we consider the system of congruences. X congruent to 1 mod 4. That's 1, 5, 9, 13, dot, dot, dot. And 2 congruent, x congruent to 2 mod 6. It's the remainder is going to be 2 when we divide it by 6. 2 plus 6 are 8, 14, 20, dot, dot, dot. I claim, in fact, there is no solution. Because if you look at this thing, this is always going to be an odd number. And this is always going to be an even number. Okay? Any questions about that? Some systems of congruences don't have a solution. That shouldn't be a surprise, because after all, some single congruences don't have a solution. Okay? Some systems do, some systems don't. Okay? And it turns out to be an important and useful thing to be able to figure out which is which. Okay? Or to solve the system if there is. Okay? Any questions? This problem of solving systems of congruences is important enough that it was actually solved. I mean, it was actually interesting. It was solved, okay, by a Chinese mathematician, okay, 1,500 years ago or more, okay, and it's usually called the Chinese remainder theorem, okay, after the fact that this guy was Chinese, okay. Any questions? I've heard it occasionally called the Formosa theorem. Does anyone know why it's Formosa and not Threemosa? Okay. The reason is because Formosa is the island of Taiwan. Okay, and that was supposedly another name for the island of Taiwan, and that was where it was supposedly discovered. Okay, but and Threemosa is nothing. Okay, any questions? Okay, so that's the history. But the Chinese remainder, it's interesting. Again, it's one of the oldest interesting theorems that is really kind of an impressive thing, and we can do a lot of interesting things with it. Okay, any questions? So what is our goal? Okay, our goal is to solve a set of congruences. We saw how to solve one congruence. That's now, if it's solvable or not solvable, that's something we can do. Okay. Suppose, let's say, that we're now given a system of r such congruences. Okay. Let's say each of these congruences has different, moduluses that are relatively prime to each other. So we got into trouble, if you look at it in the last case. We got into trouble because these things were not relatively prime. Okay? Suppose, let's say, that we are given a set of congruences, okay, where the moduluses are all relatively prime to each other, pairwise relatively prime. Okay? And we'll let M be the product of all these moduluses. Okay? Then I claim that this system of congruences has exactly one solution mod M, mod the product of all of those things. Okay? Any questions about what the theorem states? Okay? We're given a set of congruences of the form X congruent to some constant mod some other constant. So our world is specified by r such pairs of numbers, defining r congruences. My claim is these congruences have exactly one solution, mod M. Okay? Any questions about what it means? Question? What's AI? What is it? Is it subscripted for a reason, or? AI is subscripted for the same reason MI is subscripted. We're given, the Chinese Romantic system is dealing with a system of congruences. Okay, we agree that we're talking about a system of congruences. So what this is saying here is that we're given R congruences. The ith congruence is X congruent to A sub I mod M sub I. Okay? Any questions? Question? The AIs can be whatever they want to be. Okay? The MIs, okay, the moduli have to be relatively prime. Okay, and that gives us a solution. Then I claim there's only one solution to this thing. Okay? Any questions about that? Okay? Let's try to prove that. Okay? And again, it's going to be a constructive proof. It's going to give us this integer. Okay? Let's see what that is. First claim that for every one of these moduli, m divided by mj has to be an integer. Okay? Why is that? Okay? Well, by definition, we defined m as being the product of all the moduli, right? Dividing it by mj is like simply just not multiplying it by mj, right? So this should not be any kind of problem. Okay? Everybody agree that m divided by mj is an integer. And further, mj is relatively prime to m over mj. Why is that? Okay? Because now this is going to be the product of all the other moduli except mj, correct? And each one of these guys is relatively prime to mj. Okay? So this has to be the case. There can't be any factor in common, because if there was a factor other than 1 in common to these two, then that would mean that there was somewhere we could trace it back to which of the other moduli was not relatively prime to it and pin the blame down. Okay? So clearly we know that this is true and that's true. Any question? So that's true. Now I claim if I take m over mj mod m times some if I take a look at the congruence equation, the linear congruence we had before, of this times a variable is equal to this congruent to that mod that. I showed you before that no matter what, that if you have an x here, because this is relatively prime to that, there was exactly one solution to that congruence, correct? So there exists something. Once I fix this integer, and it happens to be 1, okay, there has to be some bj, such that bj times this thing is congruent to 1 mod this, because this is relatively prime to that. How many people are with me so far? Okay. Any questions? Okay. What else do we know? Let's look at the congruence m over mj congruent to bj, okay, mod, okay, suppose that this times something, okay, is congruent to 0 mod mi. My claim is that no matter what bj is, m over mj is going to be times something is going to be congruent to 0 times mi. Why is that? Okay, don't get lost in the notation. Why is this? What do we know about m? M is going to m over mj. If j is not equal to I, this is going to be a bunch of things multiplied together, including mi, right? Mi times something minus 0, I'm claiming is divisible by mi. Of course it is. Okay? So lo and behold, for any such bj, okay, this is going to be true. Okay? Any questions so far? Okay? Now I'm prepared to talk about what my integer is, the solution to all of these things. I'm going to take for each congruence, okay, remember this was defined for any given congruence J, okay, I was going to let Bj be the unique solution to this congruence, okay. Now I'm going to define an integer as the sum of over all the congruences, Aj, which was part of my input, Bj, which I just computed, times m over mj, okay, which we agree is an integer, okay. So I've got this integer, which is the sum of integers. It's the sum of integers that are the product of three other integers, okay. This I claim is my solution, okay. What does it mean to be a solution? That means that if I take this integer and I truck back to pump it into every single one of these congruences, that in fact it satisfies all of them, okay. Well, let's think about one of these particular congruences, okay. Namely, let's think what this integer is, mod mi. What do I know? This integer is the sum of r different integers. My first claim is that of these r integers, each of these integers was defined by a particular j here. Okay, it's defined by m over a different, each one of these terms has m over a different modulus, correct? Suppose, let's say, I divide m over mj, aj, by mi, where mi is not equal to, I is not equal to j. What is that going to be? Okay. What do I get? Okay, what is it congruent to? M over mj, bj, aj, divided by mi. What's the remainder? The remainder is 0. Why is the remainder 0? M, remember, up here. We said that m was going to be m dot 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 mi, okay, everything except mj. If this is mi times something, is going to be congruent to 0 mod mi, right? So we're adding up a bunch of different integers. All but one of these integers I claim is going to be equal to 0 mod mi. Okay? How many people see that? How many people don't see that and want to see it? Okay? So the only thing that's going to be left that's not going to go to, I proved basically that but one of these terms is going to be 0 mod mi. The only one that isn't going to be 0 is the case where, in fact, we've already, or isn't necessarily going to be 0, is going to be the case where mi, okay, where basically we consider the term where j equals I. So this is going to be a bunch of zeros plus m over mi, bi, ai. Okay? But what do we know about this? We know that, as shown up here, m over j, m over mi, times bi, m over bi, m over mi, times bi, is congruent to 1 mod mi. Right? I just substituted j for I. So this thing, m over mi, bi, that is congruent to 1. Okay? Therefore, we can replace this thing by 1. This is congruent to 1 mod mi. So this is going to be 1 times ai. This has to be congruent to ai. Okay? And that completes the proof. Okay? For this magical integer was constructed so it satisfies every single congruence. Okay? Any questions? I'm happy to go through that proof again if anyone wants me to. Okay? Any questions about that? Okay? It's kind of interesting. It gives us a way to compute an integer that satisfies all these congruences. Any questions? Okay? So again, let's just look at an example here. Suppose we consider the example of x congruent to 3 mod 4, x congruent to 4 mod 5, x congruent to 3 mod 7. All these moduli are relatively prime, so everything's cool. Okay, m is the product of those things, or 140. We could solve for the first one, m over, except for the first modulus, congruent to 1 mod the first modulus, we get that. Here we have m over the second modulus, congruent to 1 mod the second modulus. We've got to solve that one. M over 7, congruent to 1 mod 7, we can solve that. My claim is we get back the following integer. Okay, maybe we'll zoom out just a little bit to get the whole thing here. M, what is the integer I get? I get m over m1 times b1 times a1 plus m2 over times b2 plus times a2 plus what I'll call m3 times b3 times times a3, which was there. This, if we multiply that out and add it up, we get a solution of 59. Okay, 59 claim is congruent. What is 59 mod 4? The easiest way to see that is that 60 mod 4 would be 0, right? So 59 is minus 1 mod 4, okay? And that I claim is 3, okay? Or you could do the division. I guess, what is it? 56 would be a multiple of 4. Okay, there's a remainder of 3. 59 mod 5, again, that's minus 1 because it could be, sort of, I think of this being, if I divide it, make it 60 mod 5. Okay, the range of that, minus 1, that's 4. 56 is the biggest power of product of 7 less than 59. Lo and behold, we satisfy all of these congruences with that integer. Any questions about it? Okay? So the amazing thing is that the Chinese remainder theorem gives us a way to solve any system of congruences, and that we get a unique integer, okay, over the product of those congruences. Any questions about that? Can anybody think of a reason why this might be a useful thing? Okay? This is probably a hard thing to do. But I claim that this is actually a potentially useful thing for doing computing with large numbers. Okay? Suppose, let's say, you wanted to write a program for dealing with integers. Let's say you wanted to count the number of grains of sand in the universe. Okay? I'll say 10 to the 563. That's actually not quite right. Let's say that there's 10 to the 563 is a number you want to work with exactly. Okay? You certainly couldn't write that number out, do a normal computation on your computer with that. Why not? Because the word length of your computer is 32 bits, right? Or 64 bits if you have some fancy processor. When you want to do computation on big integers, you've got a problem. Okay, in a world where you've got a computer with a finite amount of word length, correct? Okay, integer words, you normally can only store an integer up to size 2 to the 63 before you get into trouble, let's say. How do you store integers that are even bigger than that? How would anybody do it? Does anybody have some idea how they might do it? What would be this, if you wanted to write a program for doing it, what would be one way to work with larger integers? What would be the idea that would have occurred to you before you came in here? Okay? You might have built a package that did a linked list, right? You represent each number by a linked list of digits. Okay? Now you're writing something complicated, doing huge lists of digits, doing arithmetic on that. Let me, though, show you another way to do large integer arithmetic using the Chinese remainder theorem. Suppose, let's say, I want to represent an integer. Okay? Let's say I take all the primes. 2, 3, 5, 7, 11, 13, ... I take a look at the integer x congruent to 1 mod this. Suppose I define this big system of congruences of this form. How many solutions are there to this system of congruences? Okay? These are a system of congruences. The moduli are defined by prime numbers, right? How many solutions are there to this system of congruences? 1. Within what range of numbers? Okay? There's more than one solution, but there's only one up to m being the product of those things, right? How big is the product of this thing now? Okay, 1, 2, this is probably something like, let's say there's 100, another 1,000, 2,100 or something like that. Suppose I list the first 100 primes. Okay, what is the product of the first 100 primes? Okay, it's a big number. The product of the first 1,000 primes, an even bigger number. Okay? My claim is eventually, using a relatively small number of primes, you can describe a system of equations such that each integer within any kind of a reasonable size range is represented uniquely. That's really what this congruent system does. It tells you if I give you a big system of these congruences, there is only one way, one integer, between 0 and the product of these things, okay, that is uniquely described by these solutions. Correct? So that said, you want to represent a big number. One way you could do it is to just keep track of the solutions, the residues, okay, for your given x, what is x congruent to? Okay, okay, let's go back to here. If we go back to the Chinese remainder theorem, what we could do is just keep track of the residues, okay, of each one of these things, okay? That will uniquely describe the integer, okay? And given that integer, we could then go back and, given that integer, we can now represent that integer as we said, okay? So anyone sort of got that idea? So what I'm saying now is the following. What this said is, I've got that for every one of, that the Chinese remainder theorem said, if you give me a system of congruences, x congruent to this, x congruent to that, x congruent to that, okay, there was only one integer x that satisfied all of those guys between 0 and the product of all those moduli. So now if you want to represent some huge number, how am I proposing to do it? Take your favorite set of prime numbers, take the remainder of your number, mod those prime numbers, which is a pretty easy thing to do, just to compute the remainder. That's a simple division. Now I claim that your number is uniquely described by its remainders of those primes. Okay? And so now if you want to store that number, instead of using a big ugly linked list of digits, you could just store it by remainders of mod these relatively small primes. And what I claim is not that many that long a list, or set, or array, of not that variably large remainders uniquely describes your integer. Okay? And now you can do certain computations on them. Any questions? How would you add two numbers together, okay, in this representation? Let's see if we can see that this is a useful representation. How many people sort of see what I mean by this representation? A bunch of people. What might be useful to this? Suppose I want to now write a program to add two big numbers together. How would I add two big numbers together? I've got big number 1. Let's go back to here. Big number 1, that when I take the remainder mod 2, 3, 5, 7, 11, 13. Let's say that the remainders I got were 1, 1, 1, 1, 1, and 1. Okay? This is going to be my number. Let's call this number y. Let's say I get another number. Let's say that's remainder is 1. Let's say 2, 2, 6, 9, 12. And call this x. Okay? What is the sum of those two numbers? Okay, how can you compute the sum of those two numbers? Well, we know that what is x mod y plus y mod 2 going to be? My claim it's going to be x mod 2 plus y mod 2 reduced mod 2. Correct? If the x is an mod 1, x is congruent to 2 mod 1, to 1 mod 2. What does that mean about x? It's an odd number, right? I claim if I add 1, and this is also an odd number, if I add them together, to add up this huge number, all I have to do is to say, well, 1 plus 1 is 2 mod 2, that's 0. 2 plus 1 is 3 mod 0. Okay, maybe I have to have another one, 17, 0. Let's say 0. Okay. What is this going to be? Okay. My claim here is that by adding these things together, okay, I can basically add together the residues. And that is the same as adding together the numbers. Okay? Any questions about that? Okay? I claim if I want to subtract the two numbers, it's the same as subtracting the systems of residues. What if I want to multiply the two numbers together? Okay? Suppose I know that x is congruent to 3 mod 17, and x is congruent to 4, and y is congruent to 4 mod 17. What is x times y congruent to? Well, I showed you could multiply congruences together, right? Like it or not, x times y is going to be congruent to 12 mod 17. So lo and behold, if I want to live in this world of representation, I can add things, I can subtract things, okay, pretty easily, okay, and I can multiply things. So I claim that this idea of using the Chinese remainder theorem gives me a potentially new way to represent huge numbers, okay, such that a lot of computations on them can be fast. Any questions about that? Okay. Any questions? Yes? This is actually used in, my understanding is that this is used in certain high-speed, large kind of computations. So like, for example, one place where it might be useful is in certain, like for example, cryptographic applications. Okay, you may be useful, you know, that when you're dealing with like the RSA algorithm, you're doing a lot of multiplications mod some 200-digit number. Okay, this is sort of a way to sort of do these kind of computations, I claim. I believe you can use these kind of ideas to do those computations faster than you might do in a brute force way. Okay, so the answer is for special purpose things, I think this is sort of a useful way to do it. Okay, question? So what you're saying is you're 100% right that this could not distinguish between numbers that are greater than the multiplier of all, the product of all these moduli. Okay? So you're right. I'm not representing infinitely large numbers this way.
When you add a number or when you multiply a number, how do you know if it will overflow or not?
Okay. So the concern is, what about overflow? I'll tell you, I'm not going to worry about overflow for the following reason. Yes, you've got to deal with overflow, okay? Because you're right. If you overflow too far, if you have a number that is too big, okay, this is going to represent there's only one unique solution, mod the product of these guys, okay? And if you get larger than that, then in fact it's going to think it's a smaller number. But let's get serious. I can have as many of these primes as I want, right? If you're going to tell me that the number is going to be large, but not too large, I can create, you tell me what too large is. I'm just going to slap on enough primes here so that for any number within any reasonable range for you to want to work, it's going to be uniquely defined here. Okay? And so it's not infinite precision, but it's as large as you want it to be. Okay? And because I'm going to be multiplying it by another prime each time, not that many, if I want a 200-digit number, how many of these primes do I need to multiply to get 200 digits? Okay? I believe about 10 typically. Okay, something like that. 15. You're not happy with 200 digits? You want 1,000 digits? Multiply 500 of these guys. Still not much. Not happy with 1,000-digit numbers? Make it, the point is you can add primes to make it large enough. So for any range you're interested in being, overflow shouldn't be a problem. Okay? Any questions about it? Question?
Is it easy to compare two numbers in this?
Well, let's think what you can do here. It should be easy to compare two numbers for equality in this system, because equality would be the residues, okay, the same. Can you tell whether one number is bigger than another number? Okay? This is not so immediately obvious to me. Okay? It's not obvious that just, that their remainder, that you can look at these spectrum of numbers and see which one is bigger. There may be an algorithm for doing that short of blowing up the whole numbers. Okay, but that requires more cleverness than I can immediately see. Okay? So there are limitations to doing this thing. That's why we're not going to replace all our pocket calculators with this. Okay? But it's clear that you can do interesting things with this. Any questions about it? Okay? Good. So we should have some respect for the Chinese remainder theorem. Any other questions? Let's have show some more reasons to respect this theorem. My claim is that the Chinese remainder theorem gives us another way to do something we already had started to do. Okay? Namely, we showed how to solve the Chinese remainder theorem. Okay? We saw was a way to solve systems of congruences. Okay? Earlier, I showed you how to solve a single congruence, right? Where you might have this big modulus here. I showed you how to chop that down so you could solve it for a case of a small modulus. Let me show you another way to solve a congruence like this. Okay? Suppose we know that AX is, let's say we factored the modulus. Okay? Suppose we now want to know what is the solution AX, such that AX is congruent to B mod M1, M2, MR. My claim is that if AX is congruent to B mod the product of these, my claim is that AX is congruent to B mod M1. Why is that? Let's stop and think about it. Okay? If why is that? Okay? If we know that what this means is that AX minus B is divisible by all of these guys, right? If AX minus B is divisible by all these guys, is it divisible by M1? Certainly, it's divisible by M1, it's divisible by M2, ... So certainly, if we have a solution for this, a solution to this is also a solution to that. Okay? And my claim is vice versa. Why? Well, in fact, if you want to think of it, the Chinese remainder theorem proved that it was a solution vice versa. It said that the Chinese remainder theorem said that there was a unique solution to this thing. Mod the product of that. Okay? So, in fact, we could then go back and forth. Okay? Any questions about that? Okay? So again, just to sort of see going this way, that we know that if M, the product of these moduli, divides this, that means that each one has to divide that. If we know that M1 divides this, and M2 divides this, then my claim is the least common multiple of M1 and M2 has to also divide that. Okay, let's stop and think about it. If M1 and M divides this and M2 divides this, M1 and M2 are relatively prime. The product of those two has to define it. Okay? If on the other hand they're not relatively prime, maybe this is 2 times 3, this is 2 times 4 times 5, my claim is that we know that the least common multiple of these two has to divide that. Okay? If we have factored these things are relatively prime, then in fact then we know that in fact we get the product here. And that's what it proves it the other way. Any questions? So the neat thing about these congruences is it gives us a chance to go back and, using the Chinese remainder theorem, to go back and solve, if we want to solve a congruence here, where the modulus can be factored, lo and behold, we can reduce it to a system of congruences and just apply the Chinese remainder theorem. Any questions about that? Okay. Let me tell you what. Let me stop while I'm ahead now. Any questions here? Okay. What I'd like to do now is pass out or at least tell you about the exam. Okay, and then we will. I'll then run back and put it in the back for you guys to take when you leave. Okay. The exam is a take-home exam. Okay. It is open book. You're allowed to use the book. It's closed mouth. Okay, we can actually show you what the exam is here. Okay, let's just double check this thing here. I don't know if you can read it or not. Let's zoom it in here. Okay. Open book. Okay. You're allowed to discuss it with me. You're allowed to discuss it with the TA. You're not allowed to discuss it with each other. And this is sort of important to me. Okay, that I did not want to make this an in-class exam because then there'd be a fear of time pressure. Okay, and we'd lose some lecture periods. I do not want to make this closed book, okay, because I want you to be able to refer to the book and think about these things. But it's important to me that you not work together on this, okay? Now, again, I was an undergraduate at the University of Virginia. We had an honor policy at the University of Virginia, okay? Everybody had to sign a pledge on every document saying that they have neither given nor, as my honor as a student, I have neither given nor received aid on this examination. I expect everybody will sign this pledge. It's important that you not talk to each other on this exam. Okay? If I find out that people were talking together, this is going to make me very angry. Okay? If I catch the people who are doing it, I will do bad things to them. And I will feel I can no longer trust graduate students with take-home exams. I don't feel I can trust undergraduates with take-home exams. Okay? And I wouldn't do this for undergraduates. But supposedly you're closer to being adults. Hopefully many of you are adults. Okay? Okay? So it's important to me that there not be cheating going on here, because if we do catch this, this will sort of break my soul, okay, and will hurt future generations of students and the people, ideally you guys also on the next test, okay. So what's needed, okay? There will be 6 problems on here, okay. Work each on a separate sheet of paper, okay. Some of the problems are easier than other problems, okay. Not everybody is going to get all the problems. Don't worry about it. Do the best you can. You have as much time as you want over the week, okay? My vision is it should take on the order of 3 hours for someone who's on the ball, okay? Maybe my vision is flawed, okay? But hopefully not grossly flawed. So this shouldn't be an all-week exercise. Although if you want to make it that way, you're more than welcome, okay? Don't go looking through, prowling through books looking for answers. I don't know of any book. The truth is I don't know of any book that has any of these things in them. Okay? That doesn't mean that there is no answer that exists somewhere in a book, but it does mean that it is not likely to be a productive strategy to go hunting for it. Okay? See what you can do, beat on it, do the best you can. Each paper has front and back on it. Okay? Any questions? Again, this last problem is to find some kind of a concept that's easy to understand. It's in the book. I'll probably mention it next class. Okay? But you should be able to see it in the book without any fears, without any problems there. Any questions? Okay, any questions at all? Okay, so question. Where do you turn this in? You will bring it to class next week, a week from Thursday. You will bring it here and you'll turn it in at the beginning of class. So I'll need them at the beginning of class Thursday. Any other questions? Okay. If not,
Yes.
any other questions?
Hello?
Yes.
Yeah. What do we do? Do you want to?
What are you doing at Denver? I will email you a copy of the. My plan is I got email addresses of you guys. My plan is to email it to you within half an hour from now. Okay, when I return to my office. If it is not waiting for you in half an hour, you should give me email and a hostile phone call or something like that. Make sure I get it to you. Okay, does that sound reasonable? Can you guys print both scripts?
That's okay. No, that's okay. But how do we get it back to you?
Okay, I think at the moment, let me see how you succeed in mailing me your homeworks. And based on the success of that, we may ask you to do it again. Okay, we'll work that out. Okay, anything else? If not, good luck. See you. Let me go bring these to the back of the room, and you can fight over it. Okay, hold on.